When a commercial airliner impacts the ocean at high speed, the kinetic energy violently tears apart the airframe. Yet investigators rely on a single, isolated piece of electronics to sink to the seafloor and remain completely intact. This is the flight recorder. Despite its colloquial name, the device is painted bright safety orange and wrapped in reflective tape to make it highly visible among scattered debris. The system relies on a flight data recorder, or FDR. It intercepts thousands of electronic instructions sent across the aircraft, capturing at least 88 specific flight parameters several times per second, including altitude, airspeed, engine thrust, and actuator positions. This telemetry writes to a continuous storage loop. As the flight progresses, the system automatically overwrites the oldest information to preserve the most recent 25 hours of data. A companion device, the cockpit voice recorder, monitors the audio environment. It logs pilot communications, automated alarms, and the physical sounds of the airframe under stress, also storing up to 25 hours of audio. Both units are mounted in the tail section. In a severe forward collision, the empennage is statistically the last part of the plane to impact the ground, absorbing the least amount of kinetic energy. But gathering precise telemetry is useless if the memory boards inside are destroyed on impact. The physical containment vessel has to endure kinetic forces that tear the rest of the aircraft to shreds. The internal data is housed inside a cylinder called the Crash Survivable Memory Unit. The memory boards are nested inside 3 distinct layers of physical armor. The outer armor is a 1/4-inch thick shell of stainless steel or titanium, engineered specifically to resist blunt force and tearing. Below that sits a 1-inch thick block of dry silica, designed to act as an extreme thermal barrier. At the very center is a thin aluminum housing that delicately cradles the stacked solid-state memory boards. To meet Euro-K testing standards, this cylinder must survive an impact generating 3,400 g-forces for 6.5 milliseconds, simulating a high-velocity collision with a solid surface. It must also resist a piercing attack. A 500-pound steel pin is dropped from 10 feet directly onto the outer shell to simulate jagged structural wreckage driving into the unit. Then comes a static crush test, where the unit withstands 5,000 pounds of pressure applied across every axis for 5 full minutes. Surviving the kinetic violence of the initial impact preserves the outer casing, but the crash sequence immediately introduces completely different environmental threats. To simulate post-crash fires fueled by burning jet fuel, the recorder is engulfed in flames reaching 1,100 degrees Celsius for 60 consecutive minutes. The dry silica layer traps this external heat so thoroughly that while the external interface cables literally burn away, the interior stays cool. The solid-state chips remain perfectly intact. If the crash occurs over the ocean, the recorder drops to the sea floor, where intense deep water pressure forces corrosive salt water into any microscopic flaw. To counter this, manufacturers embed industrial O-rings into the precision-machined joints and apply chemical conformal coatings directly to the circuit boards. This keeps the unit completely dry and operational at depths of 6,000 meters for 30 days. Even with a perfectly insulated and waterproofed data drive, the information is entirely inaccessible if search teams cannot locate a small cylinder in the vast ocean. Bolted to the recorder is an underwater locator beacon. The moment its external sensors touch fresh or salt water, an autonomous battery activates the system to emit a periodic ping. Historically, standard 37.5 kHz beacons provided an acoustic detection range of about 3 nautical miles. Modern low-frequency 8.8 kHz beacons expand that radius to over 12 nautical miles, radically shrinking the search grid for recovery teams. When recovery teams finally pull a recorder from the deep sea, they don't dry it off. They immediately submerge the unit in a cooler of water during transport, preventing sudden exposure to air from rapidly degrading the internal components. Inside a secure lab, investigators dismantle the damaged unit. They extract the surviving memory modules, restack them, and attach new interface cables to download the raw binary data. The sheer difficulty in recovering lost data in vast ocean environments, specifically during the prolonged searches for Air France 447 and Malaysia Airlines Flight 370, forced the aviation industry to mandate these newer, longer-range beacons. The extreme engineering required to protect these memory boards serves a practical purpose. By isolating the exact technical and human failures of a downed flight, regulators can adjust maintenance protocols and training procedures, ensuring the same circumstances never bring down another aircraft.